When you think about a machine, you probably picture rigid parts, right? Metal gears, clunky hinges, all that stuff. But what if I told you the future of mechanical design is, well, soft? What if the absolute best way for something to move isn't with a joint at all, but just by bending? Let's dive into this pretty incredible revolution in engineering.
I mean, that's the question, isn't it? It kind of flips everything we think we know about engineering on its head. We're just so used to thinking that for something to move, you need separate parts that are connected by pins or bolts or bearings. But it turns out nature has been showing us a much more elegant way to do it for millions of years. And now technology is finally letting us catch up. And this slide just lays out the difference perfectly. Okay, so on the left, you've got the old way. Tons of individual parts. That means you get friction, you get wear and tear, and you get something called backlash. That's that little bit of unwanted slop or play in a mechanism. Plus, you have to assemble it all and maintain it. But now look at the right. This is the compliant approach. A single, solid piece that gets all its motion just from flexing. No friction, no wear, and no assembly. It's just an incredibly elegant solution. So let's really get to the core of this radical idea. How do you actually build something that moves by bending? Well, it all comes down to a concept that's both surprisingly simple and unbelievably powerful.
The official term for all this is a compliant mechanism. So instead of relying on stiff parts moving at a hinge, the entire motion comes from the material itself deforming, stretching, bending, and flexing, but in a really controlled way. It's not about separate parts at all. The mechanism and the structure are exactly the same thing.
Now, what's so fascinating is that this isn't some new invention. We're really just reverse engineering what nature has already perfected. I mean, think about the wings of a mosquito, or an elephant's trunk, or even how a flower blooms. These are all incredibly advanced compliant mechanisms, and they work flawlessly without a single pin or joint in sight.
And it's not just nature. Humans have been using this exact principle for thousands of years. The bow and arrow is one of the most classic examples. The bow is just a single piece that's designed to flex. It stores a massive amount of potential energy as it deforms, and then it releases it all at once to send the arrow flying. That is compliance in action.
You've probably been using compliant mechanisms your whole life and never even thought about it. A paperclip, the little latch on your backpack, a pair of tweezers. They're all single-piece objects that work because they're designed to bend and then spring right back. They're simple, cheap, and super effective.
Okay, so beyond these simple examples, why is this single-piece philosophy such a total game changer for modern engineering? Let's break down the huge advantages that make this approach so powerful. This chart just spells it all out. Traditional mechanisms have joints that wear down, they develop that annoying backlash we mentioned, and they just lose efficiency over time. Compliant mechanisms, since they're monolithic, one single piece, they have none of that. They're inherently high precision, super efficient, and because they're made from a single part, there's literally zero assembly required. And here's the advantage that really gets everyone's attention: cost. We're not talking about a small saving here. Studies have shown that the setup cost for manufacturing a compliant product can be over 50% cheaper than its old-school rigid body counterpart. Fewer parts to make, no assembly lines. That is a huge, huge economic win. But it's not just about the money. The performance benefits are absolutely massive. You get incredible precision because there's no slop in the joints. The parts are lighter, which is critical in fields like aerospace. You never need to lubricate them, and they run quieter with way less vibration. So, here's the crucial trade-off. It's a total blessing to reduce a complex machine down into a single part, but it's also a bit of a curse because the design of that single part becomes incredibly complex. You have to be thinking about material science, geometry, and physics all at the same time. Which brings us to the next big question. If they're so complex to design, how do we actually make them? Well, the answer lies in modern technology that has just made this field explode in recent years. Yep, additive manufacturing, or as we all know it, 3D printing. It is the perfect partner for compliant mechanisms. It allows a designer to create these unbelievably intricate monolithic shapes directly from a computer model, just layer by layer. What was once impossibly difficult or crazy expensive to manufacture can now be printed right on a desktop. But with 3D printing, material choice is everything. You can think of these as different flavors of plastic, and each one has its own personality. PLA, which is the most common one, is usually too brittle. It'll just snap after a few bends. TPU is super flexible, almost like rubber, but it's often too floppy to store energy well. For a lot of people, PETG is the sweet spot. It's a fantastic compromise between flexibility and durability. And while nylon gives you the absolute best performance, it can be a real headache to print with. And hey, if you're thinking about designing your own, there are some key principles to follow. To make a flexure last longer, you want to spread the bend over a longer distance. Always, always add fillets. Those are just rounded corners to avoid sharp points where stress can build up and cause a crack. Make sure you match your thinnest sections to what your printer can actually handle. And hey, if you need more force, just multiply the flexing bits in your design.
All right, now for all their amazing advantages, compliant mechanisms have one major weakness, an Achilles heel that every single designer has to deal with: the problem of fatigue.
I mean, it makes sense. When you design something to move by bending, you are by definition stressing the material over and over and over again. And that repeating stress is the perfect recipe for one thing: fatigue failure.
This stress analysis just visualizes the problem perfectly. You can literally see the hot spots in red where all the stress concentrates every single time the mechanism moves. Each cycle weakens these points just a tiny, tiny bit until, snap, they eventually fail. And this is what makes fatigue so tricky. The mechanism doesn't break because of one big, huge force. It breaks from thousands, or even millions, of small, repeated forces that are way below what the material can normally handle. It's like a slow death by 1,000 flexes. But even with the challenge of fatigue, engineers are finding some incredibly clever ways to solve for it. So where is this flexible revolution taking us? Let's take a look at the future. One of the most exciting areas, for sure, is in microelectromechanical systems, or MMS for short. We are talking about machines on the scale of a human hair. I mean, at that size, you can't use screws or hinges. Compliance isn't just a cool advantage, it's an absolute necessity. And these applications are just exploding everywhere. In robotics, we're seeing soft grippers that can pick up an egg without even cracking it. In medicine, more precise surgical tools and way more advanced prosthetics. In aerospace, lighter and more reliable parts for satellites. And of course, in everyday products, simpler, cheaper, and more robust designs. So this all leads to a really fascinating final question. As our design tools and our materials get better and better at mimicking nature's elegant solutions, are we actually heading towards a future where the mechanical hinge itself just becomes a relic of the past? It's a flexible future for sure, and it is bending in a very, very interesting direction.